Chapter 7 is on Laplace transforms and how to apply them to solve differential equations, of course. So the first few sections are defining the different properties and concepts of what's called Laplace transforms. So here's a definition. Let's let f of t be a function on 0 to infinity. Then the Laplace transform of f is the function capital F defined by this integral. So capital F of S is equal to, let me move this down a little bit. I'll put it right in the middle because it's going to be the main focus. It is the indefinite integral from 0 approaching infinity e to the negative st f of t dt. I know maybe looks a little strange, but that's how we're going to use it. So it's going to be helpful in a lot of things, how we apply it. So the domain of f is all of S for which the integral is defined. All right, and then we have a notation for it. So it's denoted by, so F, which we don't use much, or it's L for Laplace. Let me make it a little better L. I can usually do L's pretty good because it's, my first name. Of F, well, we'll get to that in a second. So of F, and you say of S, like that. So F will be a function of something else, like X or something like that. And then when you put, or F of T is fine, is another way of writing it. But it's that L of F that is the main point of this. Okay, so let's look at a couple things. So when you do the Laplace transform, you go 0 approaching infinity, e to the negative st f of t dt. That's equal to the limit as n approaches infinity. Remember, you have to change this into this form of a limit, 0 to n, as and then you take the limit when you're done, taking the integral. So that's what we'll be doing. And what we can do, we derive some very fundamental ones and use kind of tables often. So let's look at an example of this. So example 1, let's do the simple case first. Evaluate the Laplace transform of just 1 for t greater than or equal to 0. So f is equal to L of 1, which would be the integral from 0 to infinity of e to the negative st times 1 dt, like that. So then you say it's the limit as n approaches infinity, the integral from 0 to n, e to the negative st dt. And so we know that integral, you basically, you do your u, and you're going to get the negative. So you're doing this derivative, right? You pick your u to be negative st, du is negative s dt, and then you divide by that to solve for your dt. So you get this is equal to the limit as n approaches infinity of negative e to the negative st over s, and then you evaluate that from t equals 0 to t equals n. Make sure I fit that in there. So then you get this is equal to the limit as n approaches infinity. And then you substitute in 0, you get just 1. So it's, and then I flipped it. So it's just reverse the order. So 1 over s minus e to the negative st over s. And then now you evaluate. And when s is positive, you get the limit to exist. So we say if s is greater than 0, then the limit of, and the limit of, well, no, if it's greater than 0, then this limit equals 0. That's what I'm trying to say. And then it converges. Okay, so that's equal to 0, right? I mean, you're getting a decreasing function to 0. It approaches 0 like that. And that's only if s is positive. If s is negative, then you get a negative, and then you approach infinity. So you don't want that to happen. Okay. And so you get that the Laplace transform is just 1 over s for s greater than 0. And just to be clear, this time, if s is less than or equal to 0, the integral diverges. You can't be 0. There's a couple of details here. You can't be 0, or both are undefined, right? So it can't be 0. And then if s is greater than 0, then like I said, you get the negative. Not greater. If s is less than 0, like -4, then you put a -4, you get a 4n. Well, that just takes off. So it diverges. Okay. That was probably too much explanation. You can figure that out. Okay, example 2. Evaluate the Laplace transform of e to the at, where a is a constant, where a is a constant. So this, let's see. I'll probably go and work this one out too. But then the next one I'll probably just copy. You can practice it. Let's just do that. So let's do one more where I work it out. So this is probably the steps where I'd have you guys do it. Because it's not that bad. It's good because you're just evaluating integrals essentially. So f is equal to L of e to the at. So you have two e's in there, right? It's going to be equal to the integral of 0 infinity. So you get e to the negative st, and then here's your e to the at. So that'll be able to be combined, dt. So we combine those. you get e to the at minus st dt. And you can simplify that. That's integral 0 infinity. And that's e to the a minus s times t dt. And so if a minus s is negative, then the function will be going like this, and it'll converge. So that's what we're basically going on. Okay, so this continues. Take the limit. That's equal to the limit as n approaches infinity of the integral 0 to n, then e to the a minus t dt, t dt, which is equal to, and then so now when you take the antiderivative, you get the 1 over a minus s. So you get the limit as n approaches infinity, and then, so this will be now 1 over a minus s e to the a minus st. And then you would evaluate as t goes from 0 to t goes to n. So you get the limit as n approaches infinity of, and so now you're just substituting in. You get e to the a minus s n over a minus s minus 1 over a minus s. So when does that converge? So as long as a minus s is negative, this guy goes to 0. So we want this to go to 0. So we're going to want a minus s to be less than 0, which means that a is less than s, or s is greater than a, depending on how you want to say it. So that's equal to negative 1 over a minus s, or you can write that as 1 over s minus a, if a minus s is less than 0, or a is less than s, or s is greater than a, however you want to think of that. And diverges if a minus s is greater than or equal to 0. All right, so that's basically it. So your f, then, your Laplace transform, is 1 over s minus a for a less than s. So, or you can flip that around and say s greater than a. I think that's what the book does. So you just have to see when it's going to converge and diverge, depending on your variables. And so when you're doing these, you have to picture a as a constant, right? So it's not a variable. Your t is like a dummy variable because it's just there to evaluate. But s is the function we're concerned with, function value. All right, let's look at another example. This one is evaluate Laplace transform of f of t. And for f of t equal to 2 for t between 0 and 5, 0 t between 5 and 10, and e to the 4t for t greater than 10. So we break it up, or we use 3 separate integrals. because you can do that for the Laplace transform. So you get f is equal to Laplace transform is f of t. And so you're going to get just 2 for the, so your f of t, so it would look like this. You'd say it's integral of 0 infinity e to the negative s t f of t dt. But the f of t will be those different cases, and those endpoints won't matter. These endpoints don't matter for an integral. So you're basically adding area right up to that line, but that one individual line doesn't matter. So try this one, see what you get. I'm going to show you the solution here in a second. Okay, where'd it go? There it is. Okay, so this is example 4, so it's right here. So if you have my notes already, you know where that is. So where did I go to? I think I went to here. Okay, so here's the solution. I think I just copy that and move it over. So try this if you haven't already. Won't quite fit there. It's different. Okay, so that's how you break it up, right? 0 to 5, 5 to 10, 10 to infinity, and then you evaluate, and then you get down to here again. But we've already done those integrals, so you don't have to redo them. And then again, you evaluate. This is going to go to 0 eventually, and so you need s to be, so that you got to look for that domain when s is greater than 4. And I said note the jump discontinuity. So yeah, so right here it's 0 or 2, so that's going to jump, right? That's what's happening. We'll get more into that a little bit later. So let's look at a couple of properties of Laplace transform. I'll copy these things over too, but let me talk about them. We have what's called the linearity. Linearity of the transformation. Okay, L of f of t. All right, so I'll do this theorem. So theorem 1. So let f and g be functions such that L of f of t and L of g of t exist for s greater than alpha, and let c be a constant. Then, for s greater than alpha, where they exist, we have that the transform of f plus g is equal to the transform of f plus the transform of g. So that's what we mean by linearity. You can break it up like that. Then you also have the constant multiple concept. But as you're thinking through this, picture what they are. I mean, these are integrals. So it applies to all the properties of integrals. For the proof, I'm not going to go through all the little details. We apply properties of integrals. So essentially, it boils down to this integration concept. You have that's integral f dt, integral g dt. That's essentially what you end up getting when you want to apply that. Okay, I do want to so we have a couple things to look at. So we have these two tables. These are right from the book. Let's just put them over there. So we have them. So you want to know this table. Okay. And I think the other one will fit in there. Let's squeeze that down a little bit. So this goes through the proof of it right here. Not a big deal, right? You apply the linearity concept of integration to get it. And same thing here. You got your C in here. You can basically, that C will come out. Okay, let's grab the other one. So you can derive all these basic integral Laplace transforms. These are all the basic Laplace transforms. So you want to know, you don't have to memorize, but you need to have an idea where to find this, how to look it up. So here's a brief table, as they say, of all Laplace transforms. We did 1 and 2. Then you can take a look at the rest of them as your functions. So here's your f of t. So if you put in these functions, you get these different integrals here. So take a look at that, and it tells you where it's defined, and we'll be using that. We'll be able to go straight to these as you have something expanded. You have to put it in a certain form. So if you have this form, and you'll have to write it more like this, and you gotta know what B is and know what A is, that kind of thing. Okay. Let's see what we are at. So next we'll look at the existence. When does it exist? And something called when is convergence and exponential order. And I'll take another video.